All right, so today we're going to tackle 2.2, which is about polynomial functions. Let's first talk about what a polynomial function is. So here we've got an example in general form of a polynomial function. The degree is n. So if you look here, this is the highest exponent. And the exponents go down by 1 each time. The highest exponent is called the degree. And each of the other exponents are real numbers. Moreover, they are integers. They're whole numbers, so they're positive and they're whole numbers greater than or equal to 0. If this is the degree, then the coefficient of the term that contains the highest exponent is called the leading coefficient. So the leading coefficient and the highest exponent are going to be pretty crucial in this. All right, so let's recall some of the functions that we've talked about. Here we have a constant function. Remember, this was when you basically have f of x equal to a number. This is the linear function. And recall, quadratic functions give us a parabola. Now, if we increase the degree, so here we have degree of 0, degree of 1, degree of 2. If we increase the degree, then we can get polynomial functions that can give us graphs like this one, okay, where we've got multiple maxima and minima and so on. Some examples of graphs which are not those of polynomial functions are this one and this one, right? So in a polynomial function, the graph will never have a discontinuity like this. There will never be any corners like that one. It'll be like a smooth roller coaster going up and down. All right, so one more thing we're going to recall from last lesson is that even degree polynomials are symmetric around the y-axis, and those are like the graphs of f of x squared. So basically like your parabolas, those are your even degrees. Odd degree monomials are like the x cubed, right? Where it looks like this. So even degree will look like this, like a parabola. And odd degree will look like this. So basically even degree, both ends are either up or both ends are down. And for the odd degree, one is up, one is down. All right, so let's take a look at some of these. We're going to graph 4x to the power of 6. Now remember, if it's x to the power of 6, then basically it's going to look like a parabola, but it's going to increase very, very quickly. So here, when x is 0, y is 0. And when x is 1, y is 4. And same here. Now, if I go over 2 units here, then I would have to go up 2 to the power of 6 times 4, so you can see how incredibly narrow this is going to be. All right, here's another one. This is an x cube, right? So it's going to look like this one right here, but it's got a translation. So it's translated 4 to the right, 1 up. So 4 to the right, 1 up. And since it's an x cubed, if I go over 1, I have to go up 1 cubed, which is 1. And similarly here, over and down. If I go over 2 from the center, then I need to go up 2 cubed, so 8. So that'll go all the way to 9. And here, if I go over 2 this way, I have to go down all the way to -8. So this will look like that. Okay? All right. So from here, we can clearly figure out end behavior just by looking at the ends of the graph. However, we don't need the graph to figure out end behavior. In fact, we can look at the leading term to figure out end behavior. Okay, so let's take a look at this. So if n is odd and a is positive, so let's come up with a possibility like that. So n is odd and a is positive. So for example, if the leading term is something like 2x to the power of 3, 3 is odd, 2 is positive, then it'll look like this. And you can see as x approaches positive infinity, it goes up to positive infinity. As x approaches negative infinity, it goes down. Okay? However, if n is odd and a is negative, so if I have negative 2x cubed, then as x approaches negative infinity, I go up to positive infinity, and as x approaches positive infinity, I go down. Okay? Well, same thing here. What if n was even? So what if you had x to the 4, right? And x to the 4. Now, what if you had 3x to the 4, positive? Then both ends are up, so positive infinity on both ends. And what if you had negative 3x to the 4? Then both ends are down. All right, so again, we're looking at the graph. Let's take a look at some equations, some polynomial functions. So look at this polynomial function. And what we're going to do is we're going to look at the leading term, and we're going to apply the leading term test. Now remember, the leading term is the term with the highest exponent. In this case, it's this one. And you take it with the sign. So if it's positive 3 or negative 3, you have to take the sign along with it. So if it's this one, and what I do is I write it up over here, 3x to the 4. Now what I need to do is I need to look at the end behavior of this. So I need to look at the limit of f of x as x approaches negative infinity, and the limit of f of x as x approaches positive infinity. All right, so in the case where x approaches negative infinity, I think of a negative number, any negative number. I like -1. So I say, okay, let's suppose x is equal to -1. Well, what does that make this term? Well, then I have 3 times -1 to the 4. Now, is the result going to be positive or negative? Well, since it's -1 to the 4th, it's going to be positive. So here I say, okay, that's positive infinity. Well, what about the limit as x approaches positive infinity? Well, I think of a positive number, like x equal to +1. I plug it in. 3 times +1 to the 4. The result is going to be positive. So this is positive infinity. And there you have it. That is my end behavior. All right, let's do another one. Let's do this one. This time, the leading term, which is the one with the highest coefficient, is this one. So I have -2x to the power of 5. And again, I want to find the limit of f of x as x approaches negative infinity, and the limit of f of x as x approaches positive infinity. All right, in the case where x approaches negative infinity, I pick a negative number, like -1. And I plug it into this, so I get -2 times -1 to the power of 5. And now I need to ask myself, is the result positive or negative? Well, I'm going to get negative times negative, which is positive. So this becomes positive infinity. Well, what about here when x is positive infinity? I pick a positive number, like x equals +1. Plug it in, -2 times 1 to the power of 5. The result is going to be a negative number. So this is negative infinity. And there you have it, my end behavior. All right, what do we do when we need to find x-intercepts? Well, we learned before that we have to set f of x equal to 0 and solve for x. And we've also learned that x-intercepts are synonymous with zeros, roots, or solutions. Okay? One thing that we haven't come across yet are what we call turning points. A turning point is where the function literally turns. So it goes from decreasing to increasing and vice versa. So if we look at this function, it's decreasing and then it begins to increase. So here at x equals that point, we have a turning point. We have another turning point here and another turning point there. Now, as it turns out, just by looking at the equation for a polynomial function, we can figure out the number of possible zeros and the number of turning points. So the way we do that is this. Suppose you have your equation. You figure out what the degree is. So in this case, the degree is 6. That means this can have at most 6 possible zeros and, all right, I take that number 6, subtract 1, so 5 turning points. So these are the maximum possible numbers. Now, does this graph have 6 zeros? No. As a matter of fact, it's got 1, 2, 3 zeros. That's fine. It can have less than 6. All this is saying is it is allowed to have a maximum of 6 zeros. Now, how many turning points did we decide it had? The highlighted ones say it has 3 turning points. That's fine. It can have up to 5, but sometimes in reality it'll have less. All right? So what we're going to do here is, the wording is important, is we're going to state the number of possible real zeros and the number of possible turning points. So it's like the maximum allocated number of real zeros and turning points. So again, all we have to do is go to the degree. In this case, the degree, the highest exponent is 3. So if the degree is 3, the number of zeros is at most 3, and the number of turning points will be 3 minus 1, 2. And that's that. Okay? All right, so we found the number of possible. Now it says determine all of the real zeros. So let's find the real zeros. So what I have to do is I have to get the function, set it equal to 0, and now I'm going to try to factor this. So I can factor out an x, and I get x squared plus 5x plus 4 equal to 0. So that's x plus 4, x plus 1 equal to 0. So x is 0, negative 4, negative 1. All right, there are 3 zeros, just like the equation suggests. All right, here, the degree is 4, so number of possible zeros is 4. Number of turning points, I'm going to abbreviate, is 3. Now we need to factor this. So I have x to the 4 minus 8x squared plus 15. And I've noted that this is going to factor in quadratic form, meaning once you set this equal to 0, we factor it this way. So instead of having x times x, now we're going to have x squared times x squared to make x to the 4. And now everything else is the same. Two numbers that add to 15 and multiply to negative 8 are going to be negative 3 and negative 5. All right, so x squared minus 3 is equal to 0. X squared minus 5 is equal to 0. Here, x squared is equal to 3. So x is plus or minus root 3. X squared is equal to 5. X is equal to plus or minus root 5. So again, 4 zeros, and we do get 4 zeros. All right, so this is similar. Number of possible zeros is 4. And turning points is 3. All right, so now let's factor this. So x to the 4 minus 4x squared plus 3 equal to 0. So we're going to get x squared and x squared minus 3 minus 1. X squared equals 3, so x is plus or minus root 3. And here x is equal to plus or minus 1. So those are the 4. All right. Sometimes we have a function that has repeating zeros. So for example, if my equation was such that it said x minus 3 cubed is equal to 0, well, what do I do in this case? I take a cube root, right? And so I get x minus 3 is equal to 0, which means x is equal to 3. Well, what happened? I only got 1 0, when in reality it was x minus 3 cubed, which means I should have gotten 3 zeros. Well, where did the other 2 go? Well, it turns out they're repeating zeros, right? You get x equals 3 times. We call that repeating zeros. We also call that the multiplicity. So if this 0 is repeated 3 times, then we say the multiplicity is 3. As opposed to if I have, for example, x squared is equal to 0, here I get x equals 0, but because it's squared, I get x equals 0 twice. So the multiplicity is 2. Now, whether the multiplicity is 3 or the multiplicity is 2 actually makes a difference. So based on whether this is an even or an odd number, it makes a difference. If the multiplicity is even, then the graph touches the x-axis at the point of intercept and turns around. So for example, if I have x minus 2 squared is equal to 0, and I take a square root, x equals 2, right? But what's the multiplicity? Multiplicity is 2 because it repeats 2 times. It's x minus 2 squared. Well, what does that mean? At x equals 2, there is a 0, but because the multiplicity is 2, it's an even number, it touches the x-axis at x equals 2 and then turns right back around. As opposed to if I had x minus 2 cubed is equal to 0, well, now again x equals 2. However, this time the multiplicity is 3. And if there is odd multiplicity, then the graph crosses the x-axis at the point of intercept. So in this case, at x equals 2, it's going to cross the x-axis. So it's going to come over, cross, and then go back down. It will not turn around, okay? I actually find that pretty cool. So based on the multiplicity, you know whether it's going to turn around or come right back, or come through the x-axis. All right, so in this case, let's apply the leading term test. Let's determine the zeros and state the multiplicity for any repeated ones, and let's graph the function. Okay, so to apply the leading term test, right, I first have to find the leading term. Now, this one has been factored for us, so it's good in some ways, it's bad in some others. In order to find the leading term test, I need the polynomial in standard form, so before it was factored, right? So now, if I were to start multiplying all of these out, if I were to FOIL this term and multiply it here and multiply it here, I would get a long function of which I only need that first leading term. So to get that first leading term, essentially all you have to do is multiply that term with the 3x with the x squared. So you have to do, so the leading term would be x times 3x times x squared. Okay? And if I do that, the leading term would be 3x to the 4. Now, let's try to figure out the limit of f of x as x approaches negative infinity and the limit of f of x as x approaches positive infinity. This is negative infinity. All right, so for the negative infinity case, I need to plug in a negative number into this. And let's say I plugged in -1 for x. I would get 3 times -1 to the 4. That's a positive number, so I get positive infinity. But if I plug in a negative number, I would get if I plugged in a positive number, I still get positive, so it's positive infinity. So that's the first one. All right, let's find the zeros. Now, in the case of the zeros, it's nice that it's been factored because now I could just set each of the terms equal to 0. X is 0. 3x plus 1 equals 0. X minus 2 squared equal to 0. Here I get x equals 0. Here I get that x equals -1/3. And here I'm going to get that x is equal to 2, but with a multiplicity of 2. So the way I would state my answer is x equals 0, -1/3, and 2 with a multiplicity of 2. All right, so what does that mean? That means I have a 0 at x equals 0. I have a 0 at x equals -1/3, which is right there. And I have a 0 at x equals 2. Now, the 0 at x equals 2 has a multiplicity of 2. That means over there, the graph has to touch the axis and go back up. All right, what do my end behavior information tell me? That at negative infinity and at positive infinity, the graph is going up to positive infinity. Okay, so here it's up here. Now there is a 0 at x equals -1/3 with a multiplicity of 1, which is an odd multiplicity, so it's got to cross, turn back around. Here it's got an odd multiplicity, it's got to cross, and it's got to turn back around, cross here, but turn around because it's an even multiplicity and go back up. All right, let's do that again. Positive infinity here, positive infinity there. So it comes down. It has to cross this because it's got an odd multiplicity. Now it's got to turn around to cross again, and it's got to cross through because it's got an odd multiplicity. Now it's got to turn around, touch this, and go back up. And that's what it looks like. Now you're probably wondering, oh my God, how do I know how low to make this and how high to make this? Well, that's a calculus thing. You can't do it manually. So if you're not allowed to use your calculator, you can eyeball it. If it is on a calculator section, you can plug it in and do it. But you need to be able to do the crossing through here, 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 and here. And you need to be able to know that this just hits and turns back around. Okay? All right, let's do this next one. So for the leading term test, the leading term here is -x to the 4. And the limit of f of x as x approaches negative infinity. Okay, so this is x to the 4. By now we know that no matter what I plug in there, x to the 4 is going to be positive, right? Now, the fact that I have a negative in front means that whatever I plug in, x to the 4 will make it positive, the negative will make it negative, so this is negative infinity. If you don't believe me, you're more than welcome to plug in a -1 and you'll get a negative answer. And for limit of f of x, as x approaches to positive infinity, no matter what positive number I put in there, I'm going to get negative infinity. Okay, so that's the leading term. Now let's figure out what the zeros are. So to do that, we have to set this equal to 0 and factor. Now I can divide through by a negative. And now I can factor out an x squared. All right, so here I have x squared, and I can factor this as x minus 2 squared, right? So what does that mean? That means x is equal to 0, and I have a multiplicity of 2, and x equals 2 with a multiplicity of 2. So the way we write that is x equals 0, multiplicity 2, 2, multiplicity of 2. All right, let's see how we can graph this. We have a 0 at 0. We have a 0 at 2. Both of them are multiplicity of 2. So in both cases, the graph is gonna hit the x-axis, turn around, and come right back where it came from, right? So that's exciting. So let's see how this is going to look. It says that the end behavior is negative infinity for both. So on both ends, it's going to go to negative infinity. All right, so the graph will come up, hit this, turn right back around, hit it again, turn around to hit this again, and then come right back down. All right, let me just fix that a little bit. Okay, now if you were to plug it into your calculator, you will actually notice that it hits the point 1 and negative 1, so right there. Okay, and again, there is no way for you to know that at this point without checking for the minimum on your calculator. Later on with calculus, you'll know exactly where that point is. Okay, all right, that's all for section 2, and I'll see you guys in class.